Welcome to AI Frontiers, a podcast exploring the cutting edge of artificial intelligence research. In today's episode, we'll be examining recent advances in machine learning, showcasing papers that demonstrate the remarkable progress being made across this dynamic field. Machine learning continues to transform how we approach complex problems, from optimizing large language models to developing novel healthcare applications and creating more robust AI systems. The papers we'll discuss represent some of the most innovative work happening at the intersection of computer science, statistics, and domain-specific applications. As we explore these developments, we'll identify key themes, breakthrough findings, and methodological approaches that are shaping the future of artificial intelligence. Whether you're a researcher, practitioner, or simply curious about the evolution of AI, this episode offers insights into where the field is heading and why these advances matter. To understand the current landscape of machine learning research, it's important to recognize that machine learning sits at the core of modern artificial intelligence. This field encompasses multiple research areas spanning deep learning, reinforcement learning, and natural language processing. Three primary factors are driving innovation in this space: computational efficiency, robustness, and practical applications. As these technologies become increasingly integrated into critical infrastructure, from healthcare systems to financial services, their responsible implementation becomes paramount. The growing adoption of machine learning across sectors raises important questions about reliability, fairness, and transparency, making research in these areas not just technically interesting but societally significant. The papers we'll discuss today reflect how researchers are addressing these challenges while pushing the boundaries of what's possible. The first major research theme emerging from recent papers is computational efficiency, particularly for large models. As AI systems continue to grow in size and complexity, they create significant computational bottlenecks that limit both research and deployment. Parameter-efficient fine-tuning represents one promising approach to reduce resource requirements while maintaining model performance. A notable contribution in this area comes from Xu and colleagues, who introduced AdaPEFT, an innovative method that uses Hessian information to selectively tune only the most influential parameters. This approach dramatically reduces computational demands without sacrificing effectiveness. Similarly, Guo and colleagues developed STAR, a training-free token pruning framework that significantly reduces processing requirements for large vision language models. These efficiency advances play a crucial role in democratizing access to powerful AI systems, allowing researchers and organizations with limited computational resources to work with state-of-the-art models. Continuing our exploration of computational efficiency, we see several novel approaches for resource optimization emerging in recent research. Guo and colleagues created the efficient linear hidden state reward model, which achieves performance comparable to traditional reward models while substantially reducing computational requirements. This represents a significant advance in making sophisticated AI systems more accessible. Current research emphasizes maintaining high-quality performance while reducing memory footprint, a critical factor for widespread deployment. Token reduction techniques are being refined to preserve task-critical information while eliminating redundant or less valuable tokens from processing pipelines. These advances are particularly important for enabling deployment on resource-constrained devices such as mobile phones, embedded systems, and edge computing platforms, expanding the potential applications of advanced AI systems beyond high-performance computing environments. The second major research theme focuses on model robustness, building reliable AI systems that perform consistently across diverse scenarios. Researchers are addressing fundamental challenges in model evaluation, moving beyond simple accuracy metrics to develop more comprehensive assessment frameworks. There's growing emphasis on creating systems that can identify and mitigate potential failure modes before they impact critical applications. Particularly important is ensuring consistent performance under distribution shifts, where test data differs significantly from training data, a common scenario in real-world deployments. The field is increasingly moving beyond accuracy as the primary evaluation metric toward more holistic measures that consider reliability, fairness, uncertainty quantification, and performance stability. This shift reflects the growing deployment of AI systems in high-stakes environments where reliability is paramount. The third significant research theme centers on domain-specific applications, tailoring machine learning for real-world impact in particular fields. As machine learning matures, researchers are increasingly adapting general techniques to specialized domains with unique requirements and constraints. Healthcare applications represent a prominent example, leveraging machine learning for improved diagnostics, treatment planning, and patient monitoring systems. In the financial sector, AI systems are being refined for risk assessment, fraud detection, and market analysis, requiring specific adaptations to handle sensitive data and regulatory requirements. A key finding across multiple papers is that integrating domain knowledge directly into model architecture or training processes significantly improves performance compared to generic approaches. This highlights the importance of cross-disciplinary collaboration between machine learning researchers and domain experts, which continues to drive innovation by combining technical capabilities with practical needs and constraints. Synthesizing critical insights across the research we've examined reveals several key findings. First, parameter efficiency is achievable without performance degradation. Researchers have demonstrated that models can maintain high-quality results while dramatically reducing the number of parameters that need to be tuned during adaptation to new tasks. Token pruning techniques have proven particularly effective at significantly reducing computational requirements, sometimes cutting processing needs by more than half while maintaining comparable performance. Hessian-based approaches have emerged as powerful tools for identifying the most critical parameters in large models, enabling more targeted and efficient optimization. Domain-specific adaptations consistently outperform general-purpose models when evaluated on specialized tasks, reinforcing the value of tailored approaches. Perhaps most importantly, these computational efficiency advances are democratizing access to AI capabilities, allowing researchers and organizations with limited resources to work with state-of-the-art models that would otherwise be prohibitively expensive to train or deploy. The methodological approaches employed across recent research papers reveal how researchers are systematically advancing the field. Comparative studies evaluating efficiency-performance trade-offs provide crucial insights into which techniques offer the best balance for different applications. Ablation studies that isolate the impact of specific components help researchers understand exactly which elements contribute most to performance improvements. Rigorous benchmarking across diverse tasks and datasets ensures that advances are generalizable rather than limited to specific scenarios. Mathematical optimization of computational resources has become increasingly sophisticated, with researchers developing formal frameworks to maximize performance within strict resource constraints. Interdisciplinary approaches combining machine learning expertise with domain knowledge continue to yield some of the most practical and impactful advances, particularly in specialized fields like healthcare, finance, and scientific research. These methodological approaches collectively reflect the field's increasing maturity and rigor. Let's examine one of the selected research papers in greater detail. Xu and colleagues introduced AdaPEFT, which stands for Adaptive Parameter Efficient Fine-Tuning Approach. This innovative method uses Hessian information, a mathematical representation of how the model's loss function changes with respect to its parameters, to identify the most influential parameters in a large model. By targeting only these high-impact parameters for fine-tuning, AdaPEFT dramatically reduces computational requirements compared to approaches that update all parameters or use predetermined subsets. Despite this selective approach, the method maintains performance comparable to full fine-tuning across multiple benchmark tasks. This research was selected for our review because it represents a pioneering approach to efficient adaptation of large models, addressing one of the most significant bottlenecks in current AI development: the enormous computational resources typically required to adapt foundation models to specific tasks. Another noteworthy research contribution comes from Guo and colleagues, who developed STAR, a training-free framework for token pruning in large vision language models. Unlike approaches that require additional training to identify which tokens can be safely removed, STAR uses a novel algorithm to dynamically assess token importance during inference. This approach significantly reduces computational cost by eliminating unnecessary processing of redundant or low information tokens. Crucially, STAR preserves task-critical information, ensuring that performance remains high even as processing requirements decrease. This research was selected for our review because it represents an innovative approach to runtime efficiency, addressing the computational challenges of deploying large models in production environments where latency and resource constraints are significant concerns. The training-free nature of STAR makes it particularly valuable for immediate implementation without requiring expensive retraining of existing models. The third selected research paper we'll highlight is the Efficient Linear Hidden State Reward Model, also developed by Guo and colleagues. This work presents a novel approach to reward modeling, which is a critical component in reinforcement learning systems and particularly important for aligning language models with human preferences. The innovation lies in using a linear model operating on hidden states rather than the more computationally intensive approaches typically employed. Despite this simplification, the model achieves performance comparable to traditional reward models across multiple evaluation benchmarks. Most importantly, it substantially reduces computational requirements, making it feasible to deploy sophisticated reward modeling in resource-constrained environments where previous approaches would be prohibitively expensive. This research was selected for our review because it exemplifies the careful balance between performance and efficiency that characterizes the most practical advances in current machine learning research. Looking toward future directions in machine learning research, several trends appear likely to dominate the field in coming years. Further optimization of large language models for specific domains will continue, with researchers developing increasingly sophisticated techniques to adapt foundation models to specialized applications without prohibitive computational costs. We can expect to see integration of efficiency techniques directly into model architecture design, rather than applying them as post-training modifications. The development of standardized benchmarks specifically for efficiency evaluation will help researchers better compare different approaches and understand their trade-offs. Exploration of hardware-software co-design for machine learning systems will intensify, with algorithms increasingly optimized for specific hardware architectures and vice versa. Perhaps most significantly, responsible AI practices are becoming central to the research agenda, with considerations of fairness, transparency, and reliability integrated into core technical development rather than treated as separate concerns. To understand one of the key technical concepts underlying recent efficiency advances, let's examine Hessian-based parameter selection in more detail. The Hessian matrix represents the curvature of the loss landscape in a machine learning model. Mathematically, it contains the second derivatives of the loss function with respect to each pair of parameters, revealing how changes in parameters affect model performance. Higher curvature in the loss landscape indicates more influential parameters, those that have a greater impact on model outputs when modified. AdaPEFT leverages this mathematical property to select parameters for fine-tuning, focusing computational resources on the parameters that will provide the greatest benefit. This approach enables highly targeted adaptation of large models by identifying exactly which parameters have the most impact on performance for specific tasks. The Hessian-based selection provides a rigorous mathematical foundation for efficient model adaptation, replacing heuristic approaches with principled optimization. It's worth noting how this presentation itself was created, as it demonstrates the current capabilities of AI systems. The content for this podcast was synthesized using Anthropic's Claude 3.7 Sonnet model, released in February 2025. Text-to-speech synthesis was performed using Google's latest TTS technology, which provides natural-sounding narration with appropriate pacing and intonation. Visual elements for the accompanying slides were generated via OpenAI's image generation tools, creating professional visualizations of complex concepts. Human expert review was conducted throughout the process for quality assurance, ensuring technical accuracy and clarity. Despite careful review, it's important to acknowledge that some oversights may exist in the synthesis, as is common in any analysis of complex technical material. This meta-information provides transparency about the production process and the technologies involved in creating this content. To stay updated on the latest research in artificial intelligence and machine learning, subscribe to the AI Frontiers YouTube channel. Each week, we provide research syntheses covering breakthrough papers across the field, making complex developments accessible to both specialists and those new to AI. Our content includes accessible explanations of complex technical concepts, breaking down sophisticated ideas into understandable components without sacrificing accuracy. We supplement these explanations with expert commentary on research implications, exploring how new developments might affect both the field and broader society. By subscribing, you'll join our growing community of AI enthusiasts and researchers who share an interest in understanding the cutting edge of this rapidly evolving field. Thank you for listening to this episode of AI Frontiers, and we look forward to bringing you more insights into the future of artificial intelligence.